Welcome to today's Military and Aerospace Electronics webinar, How to Apply Open Standards to Systems Using Modular Radio Frequency Architectures, sponsored by Abaco Systems, ELMA, and Science Innovations. I'm John Keller, Chief Editor of Military and Aerospace Electronics. Support for the Modular Open Systems Approach, or MOSA initiatives, is accelerating thanks to modular open standards architectures like the Sensor Open Systems Architecture, or SOSA, and the Modular Open Radio Frequency Architecture, or MORA. Adoption is helping to streamline the process of updating adaptable and scalable common compute elements for the warfighter. More specifically, support for avionics and vetronics RF systems is even more approachable. The MORA accelerates the development of open standards-based RF and microwave modules that can be used in systems enabled by the CMOSS and SOSA standards-based design for ground vehicles. MORA leverages the vehicular integration for C5ISR EW interoperability, or Victory, interfaces aligned to MORA for the Victory data bus and MORA low latency bus for data sharing. This webinar pulls together experts in hardware and software components that can be used to develop and deploy RF designs and field applications, including adaptive multi-mission reuse of these modular components. Design considerations run from the enclosure platforms designed to support the CMOSS vehicular footprints to payload cards that support mission-specific functionality to the software and firmware elements that enable the system to be ready for more compatible RF deployment. Our presenters today are Sean Fisher, Division Vice President of Business Development at Abaco Systems, Ken Grobe, Director of Embedded Technologies for ELMA Electronic, and Travis Dahl, CEO and President of Science Innovations. Let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box, and a member of our team will assist you. You also can click on the question mark Help button in the upper right-hand corner of the screen. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To ask a question, simply type it into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Military and Aerospace Electronics website within the next week. You'll be notified by email when the archive is available. Okay, so let's get started with Sean Fisher, Division Vice President of Business Development at Abaco Systems. Sean?
Thanks, John. Sean Fisher, Abaco Systems. And before I started at Abaco earlier this year, about as much as I knew about MORA was that you spelled it M-O-R-A. And I feel like that's probably the way that most of the defense and aerospace industry is in terms of their knowledge and understanding about MORA at this point as well. So, you know, why am I here? What am I here to talk about? Prior to coming to Abaco, I did have 20 years of experience actually architecting and supporting communication systems in ground vehicle and tactical systems for the Army. And so I'm very familiar with the challenges associated with all the stovepipe systems, the complexity of cabling, all the peripheral devices, the complexity of user interfaces for the soldier and their cognitive load. And so I'll be talking about some of those challenges and how the open standards are trying to address them. Well, before I do, again, I wanted to say MORA, the Modular Open Radio Frequency Architecture, and some of the constituent parts associated with it. CMOSS is the U.S. Army C5ISR EW Modular Open Suite of Standards. That's a mouthful, but basically it's trying to define standards for supporting all the mission command functions of command and control and battle management. So, as you mentioned, the sensor open systems architecture, and that's really focused on how to standardize and drive commonality and interoperability amongst the hardware components of these cards and chassis and backplane and I/O. Specifically for comms and for RF, you also have MORA and then Victory. And Victory is really about the ability to remotely manage, configure, connect, and monitor the health and status of these various systems on the network interface or the network bus within the platforms, like a ground combat vehicle or even an aviation mission system. And then MORA being an extension of Victory to really focus in on that RF chain and how you architect the interfaces between your processing card running the waveforms, the radio heads, and the antennas, etc. So, as you sort of mentioned up front, we're going to talk about, MORA and some of the RF applications and challenges associated with it. We're going to really focus in on how MOSA, as an approach, not a standard, but an approach, addresses, the RF environment and how these pieces flow together. Travis is going to give a bit of an overview on MORA and some of the core components. Ken and I will focus in on some of the hardware elements like the processors, the chassis, the backplane, and how these are enabling or supporting MORA. Travis will then go back into how the software is abstracted and how that sort of helps, tie the pieces of the various hardware and software components together. A bit about readiness. We'll go through a notional architectural application of MORA in a combat vehicle sort of scenario, and then we'll go through a summary and support Q&A. So, what are the challenges today that are really driving the open standards? Well, on one hand, we're all familiar with the near-peer adversary conversation at this point with Russia and China, and really the need to have a much faster, more robust approach to evolving technology, increasing capabilities in mission systems, and really modernize at a much faster pace. I mean, the traditional tactical combat vehicle is on a 5 to 10 year modernization refresh cycle. And clearly that just doesn't work anymore when computing technologies are advancing year over year, and probably even faster than now that we have machine learning applications being incorporated. Clearly you're going to have a lot of size, weight, and power constraints in these aged platforms like the Stryker or the Abrams or the Bradley, for example, and their inability to host an extensive electronics architecture because of limited power, and then just a lot of complexity for maintenance, for training, supporting, upgrades, logistics of the system. As an example, the picture on the right here, actually from within a Stryker vehicle, just shows, a few different radio solutions and amps and power supplies and vehicle intercom components and all the cable complexity and the nightmare that is inside these vehicles today. Continuing on with that conversation, and mentioning the whole problem of stovepiped or legacy and proprietary systems, starting with the picture on the right, this is a typical comms rack that you've got your signal officer or maybe your vehicle commander in front of, and he's trying to access all his different communication networks for command and control or for fires or for air support, etc. Display systems, different interfaces for managing, your intercom, your radio comms, your GPS information. It's just a lot of information, a lot of complexity, a lot of cabling, and a lot of individual boxes made by individual companies with a lot of proprietary interfaces. And again, it just creates a very sluggish system for adaptability, a lot of duplication where, you've got multiple radios that are effectively the same radio, but they're running different waveforms or different frequency ranges, UHF, VHF, SYNC-GARS, ATC. So it's just a lot of opportunity to reduce that using open standards where you can go to a more of a common computing environment with a common backplane to eliminate a lot of cabling, have predefined profiles for interoperability so you can more rapidly introduce new capabilities through 3 VPX cards or the technologies over time. And ultimately also making it easier for the soldier who's under duress during combat or battle scenarios, for them to actually communicate and operate without having to deal with so many different disparate systems. And with that, I'll turn it over to Travis, who will give you a little bit about how MORA is addressing the challenges.
Thanks, Sean. As Sean mentioned, there's quite a few challenges there when you're creating systems, and why we really need the open standards to really rein in that complexity and take advantage of all the advancements provided by the community. So for my piece, I'm going to talk to you a little bit about the MORA specification, how they intend to address that and how they have been addressing that, and really where they got their footing. And that was really starting with the MORA architecture, where the Army took a look at all the systems out in the field and with the ground vehicles, looking for commonalities, trying to dissect that system architecture, searching for those items that could be similar enough they might be able to be shared. And then from that investigation, it was really determined that the RF hardware was duplicated quite often, as Sean was showing in those pictures, and that there's a natural decoupling that's occurring both from a natural decoupling from the RF chain and the signal processing chain that is related to both physical constraints of the hardware and where they're placed within the vehicle, as well as the advancements in FPGAs and CPUs and how they're really pushing the signal processing chain forward to be treated more generically. And then as they evaluated that RF hardware chain, it really began to focus on how they would decompose it into high-level components with well-defined functions and interfaces for each of those components. That way you can end up with some kind of interoperable solution that satisfies and supports a variety of RF hardware. And you can see that in the figure on the right there, kind of as of a teaser, where they broke the system down into functional components, and then as you combine those different components within the architecture, as you combine those different components, that rolls up into more devices that are a combination of those components and how they turn into entities within the MORA architecture. So from the diagram there, you can see a lot of the MORA devices listed at the bottom, everything from a software-defined radio, an RF conditioning and distribution device, and a radio head. And then from there, they really wanted to dive into how can they make some quick progress with this, leveraging existing efforts within the community, and enable themselves to be successful, make quick progress, and define this interface in a way that supports existing systems as well, and treat it more as an extension rather than a brand new construct that everyone needs to follow. And you can see there kind of as the teaser, that would be Victory that they're extending, and Sean mentioned that briefly as well. So once they got done with that functional decomposition, they're really focusing on the primary objectives of the MORA specification, and we'll see here in a minute some of those and how that does a solid job of handling a lot of the challenges that have been faced, and as well as providing solid leadership focused on community engagement to really enrich the spec and foster that adoption. So now that the MORA group has the architecture kind of laid out, they moved into what are really the objectives that they want to accomplish with the MORA specification. And the ultimate primary goal for the whole specification would be the standardization of your access control and data stream management. As we all know, as Sean mentioned there, you have all different proprietary interfaces that exist within a system. It makes any kind of integration or changes within a system quite complex from a development standpoint. It's labor intensive. It kind of stifles innovation. So if you can boil it down to just purely standardizing those interfaces from all aspects, you start to unfold the other objectives that MORA was looking to achieve. And that's everything from enabling the modularization from the decomposition of the RF chain to interoperability now that everyone can speak the same language, to then being able to support multi-mission RF operations on a single platform, since you can dynamically change the approach that you have for your specific mission capability based on the fact that you can reconfigure quickly on the fly and readjust those assets to target another mission set, whether that's switching from comms to EW or SIGINT. You can move between those as well. And then additionally, the other objective was really to get back at that point of bringing the best-in-class hardware to the field. There's lots of developments within the community, and we want to be able to take advantage of those, push those out as quickly as possible, and not have these long churns of the hardware taking multiple years to get to the field. We want to be able to develop the capability and push it to the field immediately. And by establishing those standard interfaces, that enables that to be very interoperable, with upgrades being ultimately as simple as popping a VPX card out of the chassis and inserting a new one to advance the capability provided to the mission set. And then lastly, they really wanted to provide a reference design implementation to go along with our specification. And really what that was there to provide is the notion that there's a specification, everybody can interpret it slightly differently. They do their best to keep it very clear, but there might be some nuance that folks might implement a certain aspect of that differently. So by supplying a reference design, not only does that help solidify the intent by the specification, it also gives a jump start for any development, providing anything from validation of your devices or a test tool for verifying your implementation of a specific MORA device and making sure it complies with the intended approach for a MORA device. Now, once we have the objectives situated, you dive a little bit into the core structure here, and we're going to stay very high level. There's a lot to cover in MORA, and that's not really the forum here to do so. So if you're interested in the intricate details of MORA, the APG team has a great set of training materials that suggest you reach out to them to get more details. Or feel free to add some questions here that we can try and address at the end of this session here, or email any of us separately. But from the top level, the core structure is really there to take Victory and VITA-49 and find a way to extend the scope of Victory to handle additional capabilities that we now need as we're targeting the RF processing chain and decomposing that a bit. And then leveraging the VITA-49.2 spec for the message structure for data and context and command and control messages, things that are well known within the community. Both have been quite successful, but filling in the gaps of where we really need to with the MORA specification to enable a more comprehensive system solution. So when you're looking at the MORA specification, I'll point out a few things that they added that kind of goes beyond the initial Victory and VITA-49.2 offerings. And those are necessary as they decompose that RF processing chain into signal resources and processing resources, as you can see in the diagram on the right. And that's really to get at the core of resource management monitoring of those new RF devices that they've defined, as well as adding an additional data bus to complement the Victory data bus. So the new data bus is called the MORA Low Latency Bus, or ML2B, and that's there to provide a low latency, high-speed access transport for the increased high-volume digital RF data that will be consumed within a system, especially if you're sharing resources. You're going to need to be able to digitize more of the spectrum and share that throughout the system and distribute it to your various processing components. And they talk about a minimum for the more low latency bus at 10 gigabits per second, but as MORA has become a requirement for SOSA, we're looking at more like 40 and 100 gigabit per second offerings for the ML2B. You really start widening those pipes to be able to ingest a significant amount of the RF spectrum. Additionally, along with the ML2B, they wanted some low latency message-based control of that RF chain, so that way you can make configuration changes quickly. You're not slowed up by any low data rate connections, and that will help you control everything from the antenna through ADCs and DACs, as you see kind of going left to right there in the diagram, and then through the signal processors. So it enables you to do more advanced capabilities and provide better solutions for the warfighter. And then also, now that we incorporate, we're extending the scope of Victory with MORA, we need to be able to communicate with those Victory components and devices, as we showed 2 slides back. And then how are those Victory and MORA devices going to communicate together through their various components? And lastly, adding additional messaging to support any concepts not offered by Victory or VITA49. And that really fills that gap with the true functionality you need to pull a system together with this level of modularity and interoperability. Lastly, I'll kind of dive into, just given we talked about the diagram on the right briefly, but looking at that as a functional decomposition of that RF processing chain. The goal here was really to take that receive and transmit path, break it up in individual functional blocks, and then enable the developer to combine those as needed to support the various RF hardware that they have available. And then that rolls up into what kind of MORA device type are you supporting. So in a sense, they offered a flexible implementation while maintaining interoperability by providing standard interfaces for each of those functional breakouts. And that really all it does at that point is define the MORA device type that you're using. And we talked about that in terms of radio heads, RF conditioning and distribution devices, and software-defined radios. All right, so now that we've got a good understanding of, or a brief understanding of the MORA objectives and overview here, I'm going to hand you back to Sean Fisher to bring in the hardware side of things with CMFF.
Thanks, Travis. So if we step back a little bit for a moment and we use CMFF or the CMOSS mounted form factor as an example application that leverages Victory and MORA, what are we really trying to get at? Well, for CMFF, the way they're addressing the challenges with the open standards is, of course, to align with SOSA. So you've got SOSA aligned slot profiles, backplane, I/O, VITA standards for interfacing with your antennas and other peripheral devices. On the software side, Victory and MORA are there to really tie those different open standard subsystems together. So you've got your SPC card and your SDR card and your chassis communicating on the backplane, as well as communicating over the Victory data bus or the MORA low latency bus to other peripheral devices like vehicle electronics equipment or digital or analog to digital converting radio heads to the antennas, and the ability to effectively configure and manage all these different common elements running multiple waveforms. Really to do what? To support command and control, to support battle management, like your common operating picture, so that I can see my blue forces on the map and I can interact with them and share situational awareness. I can reduce swap by having, rather than 4 different individual radio boxes, I've got 1 or 2 cards running multiple waveforms simultaneously with much fewer or very fewer numbers of cable connections. I can bring in, voice and data communications for sharing PLI. I can, have my assured PNT signal coming in and then feeding all of the other system components like timing for doing, crypto communications, as well as EW and SIGINT. And again, what's perhaps the next, great challenge that everybody's working on is how does CMFF and CMOSS really fully integrate with, say, the future vertical lift digital backbone, or perhaps the ground combat systems integrated infrastructure, GCIA, and those systems. So the whole point of CMFF really is to tackle these and enable the open standards and interoperability to drive quicker modernization and more commonality moving forward. And I believe after that we are going to talk a little bit about the processing components. Obviously, I'm with Abaco. Abaco, we make 3U VPX, embedded computing, DSP, SDR, among other things. So what are the key components of these different 3VPX embedded computing components that really enable or support Victory and MORA? Well, the single board computer, which is going to be, really running your operating system and tying your battle management back into your comm systems, needs to be able to support Victory for, transmitting command and control messages across the backplane between the different subsystems, as well as potentially, depending upon your approach, multi-core single, CPUs can support multiple waveforms. So you could be actually hosting software-defined waveforms, on your SBC. The other approach being firmware-defined waveforms, traditionally on your DSP or FPGA boards. Again, the ability to run multiple waveforms simultaneously. Also to be able to do the analog to digital conversion or digital to analog conversions. And in some cases support direct RF sampling so that you can eliminate some of the other components or daughter cards or reduce the number of up-down converters necessary. And again, needs to be able to support MORA, low latency bus, as well as Victory. And the switch itself, again, having those separate control and data planes, really enabling the VDB and the ML2B separation, all of which need to be able to support Victory for the remote management, et cetera, et cetera. So a few examples, in CMFF, there's the IO intensive single board computer or SBC profile. Obviously you can see what that particular profile, SOSA profile is. As I mentioned, depending upon your approach, you could have a multi-core SBC running, 2 to 4 to possibly even 10 different waveforms on a card with today's modern, multi-core CPUs. It supports the separate control and data planes based upon the slot profile. It's also important for the whole battle management services to support multiple different types of I/O coming in from your various types of peripheral systems, like your GPS signaling or USB interfaces to other computing elements, et cetera, and potentially even an XMC site so that you can have a daughter card on there for doing graphics processing or maybe a unique type of I/O that isn't resident on the board. The other approach, again, that digital signal processor or FPGA-based firmware-defined waveform, obviously can host that in multiple waveforms simultaneously, again, aligning with SOSA and the particular slot profile, the payload profile within CMFF. A couple of different approaches, whether it be RF system on a chip or MP system on a chip. In this case, we're showing the VP431, which is an RF SoC and supports direct RF sampling. It has the A to D, D to A stuff built into the card, and so that helps eliminate some of the other components within that RF chain. And, with an MP SoC, the other option, you would have, an FMC site typically where you could have a more customized or flexible approach of different combinations of A to Ds and D to As as necessary. The network switch, again, SOSA aligned. CMFF calls out the particular slot profile, as you can see, separates the VDB and the ML2B, creating those fat and thin pipes, and potentially even supporting, optical front panel connectivity. which is another, I think, challenge within CMFF today anyway, is, with all the cards on the back plane, and then how do you get to those vetronic systems like the VDB switch inside the vehicle, or perhaps the FAF, the future vertical lift backbone, basically, through a different front panel connection. So we'll go ahead and let Ken from Elma talk a little bit about how you take those cards and put them together and start to tie everything together physically.
Thanks, Sean. So as we've come through this, we've given the high-level view of how to decompose an RF chain and what the overall architecture of that is relative to MORA. Now we're going to put more towards sort of the physical and what we need to do to connect those building blocks, or PICs as they're called in SOSA, payload interface card, and actually implement a topology that supports the MORA transport and exchange of information. So we take a look at the blue block here that has the two black chassis. These are compact frames or development chassis that hold a backplane and give you I/O to get things in and out, like antenna connections and test points, and be able to connect up your chassis manager and things like that. So what we're doing here is enabling development. And then to the right of that, what we have is a deployment chassis that's ruggedized that meets something called SAVE, which is the footprint or envelope that a chassis can take in the vehicle. So what we're showing here is the ruggedized implementation, and then this is a demo view of this with a front panel removed, so you can see the slots where the payload cards actually plug in and implement capabilities. So to do this, one needs some topology that maps the signals between the profiles back and forth and within the network. And these topologies have been developed to now be cast into off-the-shelf solutions that follow the architecture. So this topology diagram down here is showing sort of the mapping or interconnect that's required by slot to implement an infrastructure that supports MOSA and supports the VITA and the SOSA references to these topologies. So what does the backplane do? Backplane is basically a circuit card that interconnects the individual slots. And this is sort of a special circuit card in that the data that's moved in it is moving at very high speeds. It can move slowly or it can move extremely fast. And when it does that, we need to organize this data into what's called planes and then implement it for transmission across the backplane. So what makes use of this are the SBCs, the payload cards, and also the power supply cards. And they're not shown in the topology as it's represented here, but they're off to the side, and they're also standardized and can provide power right into the backplane. In addition to that, we also have chassis management, which monitors things like voltage and state and provides messaging about the health of the cards that are in the backplane, and software that goes along with that. So the key to this is that the data plane and control planes are mapped specifically to achieve some level of communication across the network. So the key thing that the chassis does today, or the topology, is to provide the network infrastructure that's used to communicate RF information, in this case when we speak of MORA, and control and command messages that take place over Victory, through the backplane to provide communication end-to-end between the payload cards. So this network infrastructure is critical to the implementation. As Travis has mentioned and Sean pointed to, MORA uses the high-speed part of this called ML2B, where the 2 in the ML2B points to low latency, LL. So this is where we're moving data quickly to transport it across the devices so it can be further ingested and processed. These standards that we reference are developed and represented through in VITA. And VITA actually contains the definition for the profiles that we're discussing, and in certain cases, the topology diagrams. Not always, but there are key reference topology diagrams that are also in VITA. So ultimately, the development chassis provides an increased speed of integration by providing a reference chassis to be able to implement capabilities that utilize MORA. So if we look at this at a next sort of a higher level, again, in a demo topology where we have switch infrastructure, a processor to the right, the 3511, and then the RF transceiver, we need to make those key connections to implement the network for VDB, Victory Data Bus, and also the ML2B, the MORA low latency bus. And here we're showing that going up to speeds of 40 gigabits. Ultimately, it will be able to go to speeds of 100 gigabits, and it's functionally required to support at least 10 gigabits. So to do that, we have two constructs, a fat pipe, which is 4 lanes, and an ultra-thin pipe, which is just 1 lane, receive and transmit. And if you look at how they map to the MORA constructs below, we see an MSRP generator, which is a tool that generates a resource profile. But when we look at these blocks within the MORA resource, you have a MORA device connected up to the VDB, a MORA resource signal manager that's also connected to the VDB, and then we have a MORA signal port manager that's connected up to the ML2B. And to the right of that, what we have is a tool called MORA Explorer, which is a user interface that actually is capable of interfacing to the messages that are within MORA and the constructs to be able to give you a visual tool to be able to interact with it. So following that, looking at a more, let's say, VITA-esque diagram, we're showing here the control plane implementation, which is where Victory would be running and where messages are communicated, and that's over what's called the control plane within VPX. And then to the right of that, we have an entity called the system manager that's communicating in that network to a chassis manager that implements chassis management function. And below that, we've got IPMB-A and IPMB-B. These are the intelligent platform management connections that allow chassis management signals to be sent or messages back and forth across the backplane to the payloads that are installed in it. So pointing to the topology a little more specifically, on the left we have the topology, on the right we have profiles. And these profiles are represented within OpenVPX or Vita65, and they're standardized. The great thing about that is one manufacturer's implementation can plug into the same profile as a different manufacturer's implementation, and they're all going to be wired out the same way or pinned out. So the ICDs are common. This wasn't the case before, which made making systems much more complicated, and it did not promote interoperability. So at the hardware level, this establishes a way to enact an interoperable implementation. So just stepping through those profiles, we have the IO intensive, the primary payload in the blue and the gold, and then the central switch with the gold and the green, and then the timing card, which is off to the switch on the left for implementing PNT solutions. So where is the ML2B? The ML2B gets implemented on the gold blocks where we have the data plane implementation in a fat pipe and an ultra-thin pipe, and below that, the VDB gets implemented on top of the control plane, which are the green boxes. So we pointed the description here in the diagram and then show you a physical implementation of that below, which is an actual backplane. So bringing this all together, we now have talked about open standards that enable VPX cards covering the RF processing chain chassis and backplanes to house this and to give you structure. Backplanes enabling connectivity, but what we need to look at next is how we abstract that interface to the hardware and how we provide the implementation in software for the functions that MORA actually provides. So I'll hand that back over to Travis.
Thank you, Ken. Yes, at this point, we have the cards in the chassis. They're powered on. All the electrical connections are made. They're physically in the right locations. And now we need to apply the MORA specification to MORA align those cards. That way we can start talking between the cards. We can get command and control. And we can start using that standardized language that we need to enable these cards to do various mission sets. What does that look like? Well, the start is taking the MORA spec, applying it to the card. If you kind of look at the diagram on the right, that gives you a brief abstracted view of what that would look like on the card, where you have your standard hardware API interfaces there for whether it's the drivers to control the various hardware components on your card, or any kind of other software that is there to enable the existing hardware before MORA is applied. So then you take MORA and you put that as your hardware abstraction layer between the existing constructs and the outside world. So now you take all those vendor-specific APIs and you turn those into MORA interfaces to allow standardized control. Additionally, you need to work on the MSRP, which is the MORA signal resource profile, to set up the capabilities for the card. And that's basically, think of it as like the digital data sheet for all the specific components that are on the card, like how many tuners, how many DDCs, how many ducts, what are your limits for each of those? Are there certain frequency ranges you can tune to? What are the sample rate bandwidth constraints? And then lastly, finding a way to be able to engage with those devices, kind of as Ken talked about earlier. Our MORA Explorer UI would enable you to talk to those devices externally. So now you can start to put your full mission set together. Maybe you can look at plotting some data, but really kind of commanding and controlling that entire system. And then lastly, kind of pulling that all together, we've covered the chassis from stuff Ken talked about. We've talked about the VPX cards that Sean discussed. We talked about some of the MORA aspects from some things science are doing, and really it kind of turns you into this notion of being MORA ready and what it really takes to get to that point, so that way you can start to de-risk the engagement with these devices. You can really turn into a situation where you're reducing timeline and cost, giving all the supporting infrastructure. And then you start taking the open standards and using them for everything they were meant to support. And from the chassis side, that's a CMOSS or SOSA chassis with a backplane supporting all the connections between the cards. That's likely some combination of VPX cards that generally falls in the realm of an RF transceiver, some kind of switch, and then a signal board computer for waveform development, whether that's EW, Cyber, SIGINT. You're looking for a generalized platform to apply there. And then from the MORA standpoint, you really need a couple of things. That's everything from an implementation of the MORA spec, both in software and firmware, similar to Science Helix Core, to enable the development of a MORA-aligned VPX card. You need some mechanism for defining the MORA signal resource profile with ease. They can be quite complex, and you need to do that for each card, and it affects not only the vendor, but also the system integrator as you're lining up the physical connections for the system. And then lastly, some mechanism to engage with that through something like MORA Explorer UI, or alternatively, a development library like Science Helix Client Core, so you can build up your own custom application, whether that's a command line interface or a custom UI. And then if you can kind of bring all those together from all these partners in the spirit of open standards, you really start to leverage the power behind those systems and being, in a sense, MORA ready, and having that MORA ready environment there for you to support. And with that, I'll hand you back off to Sean to talk to you about an example.
So We're going to go through this quickly so we can leave a fair amount of time for some Q&A at the end. But this is a notional example of a tactical communications platform. Think of it as maybe a JLTV or a Stryker or an Abrams. And bringing in CMFF as the mission package that's going to be hosting your software-defined radio card. It's going to have the SBC with the IO intensive profile. It's going to have that switch for the common computing environment in the chassis, as well as tying into the vehicle electronic systems. All using, again, a CMFF reference architecture for the backplane, for the IO, for the slot profiles. And if you follow from the common chassis down through the VITA 67.3 interface for the Aperture H to really the external MORA devices, which in this case, simple representation of a MORA radio head on the left that supports two different frequency ranges, another MORA radio head on the right, which supports yet a different set of frequency ranges, and then the actual antennas associated with those frequency ranges, ultimately supporting comms to three different radios or really radio waveforms or frequencies from one common card. So if I'm a soldier, I'm in my platform, I put on my headset, I got my push to talk, I'm connected to my intercom crew station, I can from my device, switch between the channels that I want to transmit or receive. I can press my PTT and transmit, and that's going to go through the intercom hub, over Ethernet, down into the CMFF chassis, over the Victory data bus, and it's going to then go through the system and get processed and distributed out to the SDR waveform to the external radio network outside the vehicle. And really, this also, through MORA, enables a soldier the ability to remotely control the radios within the SDR card. So now I've set up multiple antenna connections and radio heads in a common card with different waveforms. I can change frequencies that I want to use. I can change presets. I can change transmit power levels. All of this open standards-based solutions, all of it enabled by Victory and MORA, and reducing a lot of cable complexity, or reducing a lot of user interface complexity, and really ultimately going to that goal of being able to modernize faster, reducing swap and complexity. And in summary, again, what we've kind of gone through today in terms of the benefits, obviously the open standards approach allows you to really have more flexibility in terms of RF applications, more of a structured approach that supports modularity of different components, no standalone stovepiped systems that rely on a particular vendor to support. You've got all the necessary hardware elements, you've got the software elements within Victory, within MORA, you've got all the development tools and libraries to support, developing these solutions. The speed at which all this can happen is much faster. And really, Linux is referenced here as an OS, but there are other options as well for your operating system environment. So I think at this point, come see the Abaco Elma Scions team at AUSA. Here's our booth numbers. We are going to be doing a demonstration, a live demonstration that shows you some of what we had depicted in that diagram. Feel free to reach back out to us to learn more about that. And with this, thank you for your time, and we'll turn it back to John for Q&A.
Okay, well, thank you, everybody. A few of you have already submitted questions, so we're going to jump right in. If you would like to submit a question, type the question into the Ask a Question box and hit the Send button. Also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. So the first question, and it's a question for Travis, is how does MORA relate to victory?
Sure, thank you, John. So we touched on this a little bit throughout the presentation, and there's certainly more to it that we could probably answer everything here, but MORA is an extension of victory, but it very much works in tandem with victory. So in a traditional system, you would leverage victory for your broadcasting that you exist within a network for your MORA device. You would advertise your capabilities. Users would also leverage victory to reserve and release resources within the MORA device. And then that also helps point you over to the right endpoints within MORA, so that way you can then start command and controlling the specific resources that you've reserved. And that enables you to get your hardware up and running, get your knobs turned to the right location, and then to get data flow started. So they are two different specs, but they're very much tied together in a sense in that they support each other directly throughout a system.
Okay. Ken or Sean, do you have any thoughts on that?
No, I think Travis did a good job of answering it, and we kind of touched on a little bit of it during the overview.
Okay. I have a question for Ken, and that is, are there off-the-shelf backplanes that support CMOSS and MORA? Ken, what do you think?
Yeah, there are. As the ecosystem looks at topologies that are necessary that address the payload switch infrastructure and the SBC profiles, the ecosystem's responded to that, and there are a number of suppliers that are making backplanes that are built that way. Elma's worked on backplanes, the original CMOSS reference backplane that found its way into OpenVPX, and then we continued that tradition to build reference backplanes that hopefully are leading, that help the community support development.
Okay. Anyone else have anything to add to that?
Nope.
All right, then we'll move on. I have a question for either Sean or Travis or both. Are boards or PICs available that directly support MORA interfaces?
So I'll take that, and the answer is yes. As an example, Abaco and Science have worked together to deploy MORA on, our VP431, which is capable of running multiple waveforms simultaneously on a 3VPX card. And again, a lot of the other things that at least we do at Abaco are focused around victory and CMOSS and SOSA and being compliant with the standards that are being sort of required in today's industry.
Okay, anyone else? All right. Well, I have a question from the audience at our friends at Georgia Tech. And what are some of the challenges and risks you could identify with adapting MORA software to existing communications waveform applications? Anyone like to take that one? Ken, what do you think?
I don't know, Travis, do you have some thoughts on that?
Sure, I can talk to it briefly. So kind of the biggest challenge is really getting an RF transceiver MORA aligned, and then bridging that MORA interface to whatever other waveform you're doing. And Science is participating in an X-Tech waveform challenge right now with X-Tech and Viavi, where we're bridging MORA and SCA. In that instance, we're leveraging our Helix core to MORA align the RF transceiver. And then for bridging MORA to SCA, we're using our Helix client core to be on that client side where we can orchestrate the MORA device and then integrate that with whatever the specific waveform constructs would be, in a sense, creating that bridge. And then longer term, I think SOSA is going to stand up more in the determination of how those waveforms and applications are maybe controlled from a higher level. But for the current moment, leveraging MORA and the Helix client core that we're using really gets you where you need to be. We've gone through that design pattern and enabled, in this case, push-to-talk type waveforms like P25 and DMR to enable that full processing chain. So you're really kind of, in a sense, limited by, are there any specific hardware components that are needed to execute your waveforms, or could they be treated generically from a software FPGA standpoint, such that you can integrate them nicely within MORA?
So,
Okay, anyone else?
I just want to add
Go ahead,
to
Ken.
that with respect to the risk that's there. Really what we're trying to do in industry is burn that risk down, or give a platform that's a reference. And when you look at the hierarchy of things we've talked about today in this reference abstraction layer to, let's say, an aligned version of MORA back to a function that may already exist, really trying to provide folks with a path forward on that, if not all the expertise is there. And then really let's eliminating sort of the science project part of it, where we're coming up with a known reference hardware implementation. And then if we point over to Sean, in certain implementations and processors, they really get you building blocks that can get your capability developed, which is in essence what happens with the waveform that is either in existence or it's being developed.
And I was going to add one quick thing. I know we want to get some more questions in. We didn't really touch on, encryption or anything like that on our particular examples today, but certainly, some waveforms are going to have a red and a black component, and how you separate those, how you, have a common sort of control mechanism. And then some waveforms, just the frequency ranges are going to be dramatically different. So, the different types of MORA devices themselves are going to vary depending upon the waveform. What else we got?
Okay, well go ahead.
I was going to say, what else do we have for questions?
Well, that is a segue into our next question, and that is, how is cybersecurity addressed and/or mix and cross domains supported?
So,
who'd like to take that?
At a high level, I want to comment in general that those considerations have been part of the architectures over time. And let's say the question references domains. Domain separation and acknowledgement of multiple domains has been thought through the architectures. I think drilling down that further in an open forum like this may not really be appropriate, but certainly there can be some offline conversations about that to reflect what's been considered and where the resources are to go take a look at that stuff.
I'll add one thing, and just that at Abaco we have been working with some partners who specialize in that particular area, and there are multi-level security considerations being given to CMFF, for example, and happy to go into those in more detail offline as necessary.
Okay. We have a question from our friends at Raytheon, and that is, does MORA and SOSA limit exportability for international customers with MORA and SOSA-based designs? Who'd like to take that?
I could probably talk to the MORA side, but then I'd lean on Sean and Ken for the SOSA aspects, if that works.
All right.
So from the MORA aspect, we were just going through that here recently and talking with John Nielsen at APG. He's in the MOSA management office. He handles a lot of the export type things related to MORA, and the goal for MORA is that it is going to be dist A, that they want it to be sent around the world. It can be a spec that can be on anyone's desk. And 2.5 is great for that. That's the latest released version of the MORA spec. So we are able to, right now we're working with a customer in the UK to support MORA for their application. And then, you know, as the spec evolves into 3.0, you start to get into a little bit different situation where there's certain aspects of the spec that are dist D, but they're trying to work through that and see how they can open that up to be exportable to customers internationally.
Okay. Well, I can see that we're up to the top of the hour, so we still had some questions from the audience, and for those questions we didn't have time to answer, we'll be getting back to you via email. So I'd like to thank our presenters today, Sean Fisher, Division Vice President of Business Development at Abaco Systems, Ken Grobe, Director of Embedded Technologies for Elma Electronic, and Travis Dahl, CEO and President of Science Innovations. So thanks for coming. I'm John Keller, Chief Editor of Military and Aerospace Electronics.